Why is electricity transmitted at high voltage? Here's an example of a power station that's producing 500 kilowatts of power at about 25,000 volts or 25 kilovolts. The voltage is stepped up to 275,000 volts or sometimes 400,000 volts, but for this one we'll go with 275,000. Now to calculate the current flowing down the transmission lines, we're going to use Watt's law to take the power divided by the voltage and get a low current of about 1.81 amps. To get this, we'll do 500,000 watts divided by 275,000 volts. That will equal 1.81 amps. So for example, the resistance to the conductor is 10 ohms in this scenario. If the resistance is 10 ohms on the conductor, let's work out how much power we're going to lose along the way. We'll use this formula and square the current, then multiply it by the resistance. So 1.81 amps squared times 10 ohms is 32.7 kilowatts, or 32,000 watts. 32,000 kilowatts is considered a minimal power loss over a long distance within the national grid's scope. What if we generate at a lower voltage? So let's do a fictional scenario where we step the power down to 230 volt and find the current generated. We will divide the power 500,000 watts divided by 230 volts and get a large current of about 2,173 amps. Now 2,173 amps is a massive leap from our 1.81 amps, and we'll need bigger conductors in place to accommodate this, which will have a knock-on effect on pylon size. We will now use the formula and square the current, then multiply it by the resistance. So 2,173 amps squared times 10 ohms is 47.2 megawatts, 47.2 million watts. So comparing the power losses, with a step-up voltage, we get much less power loss than stepping down the voltage. With stepping up to 275,000, we get 32,700 watts of power loss. By stepping down to 230 volts, our power loss is 47.2 million.